It is 11 o'clock and it's time to start. Good morning. Excuse me. My name is Maren Mahoney. I'm a senior technical instructor at Sunset Learning. And I'm giving a series of webinars this week revolving around encryption. This is one of those things that a lot of folks find kind of scary because if you do it wrong, it can be pretty scary. But the goal, if you attend all 4 sessions, is that you'll have at least a handle on what the different components are in Cisco Collaboration for encryption, hopefully a good handle on the terms. I find for myself when I'm reading documentation that just knowing what the terms actually mean, it's like I kind of have a concept, but like what are they actually saying when they say CTL or ITL? So I want to talk about that. So, and that's really where we're headed today. So let's see. So that's our session overview. This particular webinar, this one this morning, is introductory. I'm going to be talking about how encryption works. We're going to talk about symmetric versus asymmetric encryption. We're going to talk about, and then how does that work in the real world? And my example is going to be online banking. I'm going to draw a diagram of how I can securely connect to my bank and know that I'm going to be fine. And nobody's going to steal my information as I'm interacting with my bank. So what we're going to talk about again, encryption, basics, how does it work? What are the terms? What are the different kinds of things? What's a key versus an algorithm, etc. We're also going to look at the difference between what encryption is and what a hash is. And they're both important and are both used, for instance, when we're doing something like online banking. You may have heard the term PKI or PKI certificate. Something to know, PKI is really a method of distribution. It's not the certificate itself. We talk about, there's actually more than one way to distribute certificates. And I'll talk a little bit about certificate signing requests and certificate authorities. In the next session that I'm going to be doing later on this afternoon, we're going to be taking a deeper dive into a call manager, IMP, and Unity connection server, and looking specifically at what certificates are there and what are their purposes in life. And I'll also demonstrate generating a certificate signing request for call manager and getting that signed by a certificate authority. And then again, sort of what does that mean? What impact does that have on my system? And then at the tail end, all of this talks about, again, encryption basics. At the tail end, we're going to talk about how this impacts endpoints. If you've been around Cisco Collaboration devices for a while, you'll know about an ITL, and you know that, if I'm going to move a phone from one cluster to another cluster, I have to, remove the ITL. But what is in it? What actually is this thing? And if you've heard the term CTL versus ITL, what's the difference? And this other animal, TVS, which doesn't get talked about a lot, but is actually really essential to secure operation of your devices. So this is where we're headed today. Following the presentation itself, there's a Q&A session. So if you have any questions about stuff, and feel free to jump in if you have got a question. Feel free to just go off mute, jump in and ask. And then we can talk at more length if you have a longer question or a different question after the session. So here we go. So this is the list of terms we're going to talk about today. Plain text versus ciphertext. That one's pretty easy. If you've even remotely brushed against encryption, sort of what this means already. We'll talk about encryption algorithms and encryption keys and how they're related. We'll also talk about hashing. And what the current thinking is on hashing, and again how that is part of our encryption scheme. And then symmetric versus asymmetric encryption. This, again, I don't think this is a particularly difficult concept, but if you've never seen it before, here we go. And then the other parts. Encryption in action. When we talk about SSL, secure socket layer, and the fact that it is decremented in favor of TLS, why is that? What difference is there, and what versions of TLS are there, and why do we care? This is I'm going to talk about that a little bit. And then another example of where encryption is used, IPsec VPNs. And again, I'm going to use my online banking example to talk more about this. So plain text versus ciphertext. This is a pretty simple thing. I need to send information securely to another entity. So I am going to use a key and an algorithm. The algorithm is the process, the key is the code that's used, and generate some kind of, where's my other pen? I'm looking for my drawing pen here. Oh, there it is. Sorry. So then what I'm going to end up sending, that was weird. I'm going to end up sending this to the other end. Now, they are going to hopefully have the same key that I did. And that's, the key portion of all of this is this encryption key. If I'm going to have two entities that are going to be encrypting and decrypting data, then we have to agree on a key, because that's how the encryption happens. The algorithms are open to anyone, but the key needs to be either session specific or host specific, but something. So on the other end, of course, they'll take the stuff I sent, pass it back through the encryption algorithm, but this time the decryption process using the decryption key. And notice I say that separately. There's an encryption key and a decryption key. In a minute, we're going to be talking about symmetric versus asymmetric. Wow, that is not working for me today. Let's try that again. Encryption. Symmetric just means that we're going to use the same key on both sides. Asymmetric means we're using different keys, one key to encrypt and one key to decrypt. So they don't have to be the same key. That said, one is going to be much, much faster than the other. So encryption algorithms, this is the algorithm, that's the method, the process that we use to take data and turn it into some kind of cipher, encrypted format. You may, if you are around for very long, you'll probably hear references to DES and triple DES. I don't remember what DES stands for, but this is some of the oldest encryption methods we have, developed in the 70s, DES was. And it would use a symmetric key, which means you and I would both have to have the same key. And it passed data through the key, and I could decrypt. The problem with DES is that the key itself was pretty short. And this meant that it was actually hacked. I mean, DES came out in something like 1976, and then, right, so DES in 1976, and then it was broken pretty fast. So not too far along the heels of that was triple DES, and with triple DES, it basically just did DES 3 times, as the name implies. And even at that, I'm talking about this from a historic basis, in case you, run into this. What we're doing these days, and there have been a bunch of other algorithms out there, but what we're doing these days is something called AES, Advanced Encryption System. And this is definitely a term you're going to hear. And you'll see AES 256 and AES 2048 and all this. The NSA back in the late 90s, early 2000s, put out a competition saying, hey, somebody come up with the best new way of doing encryption. And AES was the thing that won. So this is what we all do now. And AES, one of the things it does is it will take whatever your data is, chunk it up into pieces, into blocks, they call it. And then each block is treated basically differently based on how the algorithm works. And there's all sorts of components that go into this. And so it is extremely secure. It's very hard to break. Brute force attacks, you'd take supercomputers lots and lots of time to make it go. That's symmetric though. With AES, this means again that we're both going to have the same key. With asymmetric, now we're talking about a different key to encrypt and a different key to decrypt. RSA, really, really common. You probably, if you've been on a Cisco router, you may have generated or seen an RSA key in order to do SSH with that router. That's because this is what we use. If you're going to be working with something like TLS, that's going to be using the RSA as part of its thing. And then ECC. It's elliptical curve, that's right. Elliptical curve ciphering. It uses some different mathematical algorithms to do the encryption and decryption in both cases. I'm going to have a pair of keys. They are complementary. One encrypts, one decrypts, and vice versa. But you cannot use the same key to both encrypt and decrypt. So those are the algorithms. The key themselves is the string that I use for scrambling and unscrambling. Generally speaking, with asymmetric keys, they are generated once and used many times. With symmetric keys, generally speaking, we're going to be generating new keys every time we want to do a new encryption session. And the reason for that is that, it has to do with how we get keys into places. And here's an example. So you've got your PC and you want to connect to your wireless access point at your house. So on the wireless access point, you type in a password, and then on your PC, you type in a password. Now, your computer is going to use AES encryption to talk to your access point, but it had to have the key in the first place. So pre-shared keys, if you see PSK also. So in that case, because I'm talking about, me personally putting the key in both places, I can trust that, my key is secure. But in a large way, how do I see to it that keys that I use for encryption are, secure as I transmit them? And that's, we'll talk a little bit about web of trust and all that good stuff in just a little bit. So key exchange is crucial as part of encryption. And I saw somebody put something in chat. Let me go grab it and see what that was about. Data encryption standard. Thank you. DES is data encryption standard. I appreciate the thought. Thank you. All right. So then how do we go about doing all of this? Before I talk more about encryption, I want to talk a little bit about hashing. A hash function will take data, pass it through the hashing algorithm, and it will produce specifically something called a message digest. Why is my pen misbehaving? I don't know. Message digest. The message digest is fixed length. It doesn't matter whether I put in 4 characters or 4 gigabytes of characters. If I pass that data through the hashing algorithm, I will always end up with the same sized message digest. And here's the great part. Any change to the data, even one little tiny thing, will produce a vastly different message digest based on the way that the algorithm works, the hashing algorithm. So this is not encryption, and that's what I want to get at. Hashing is not encryption. It is used to verify the integrity of data. If you are downloading an ISO file off of Cisco's website because you're going to be installing a new version of Call Manager, let's say, or if you need to verify a certificate, as we will talk about shortly, then you download the file, and on Cisco's website, you will see a hash for that file. On your PC, you can run this image that you've just downloaded, this 4 gigabyte image, through the same hashing algorithm. And if the hashes match, if the message digests match, then you know that it was downloaded successfully. And again, if there's even a little bit of corruption in that ISO file, then the hashes will not match, and you have to do it again. And that's what we're talking about. So it's verifying integrity of data. MD5 has been around forever and a day. If you have worked on Cisco routers for any length of time, if you're old like me, you've been working on them 10 or more years, back in the day, if I went into my Cisco router and I told it to encrypt the passwords that are on it, it didn't encrypt them, it hashed them. It hashed them using the MD5 hashing function. And so I would get this, what looked like gobbledygook to you and I. But for short pieces of traffic, or short pieces of data like passwords, MD5, was possible to reverse engineer the actual password because of the way that MD5 works. Collisions especially, and they're talking about collisions where 2 different sets of data will produce the same message digest. Excuse me. So a collision is where 2 different sets of data will generate the same No, I can't finish my own sentence. A collision is where two different sets of data will generate the same message digest, and that's a problem. But MD5 was a little more prone to that, and because of that, it was possible, again, to decrypt. So we don't use that anymore. We use nowadays SHA. SHA is actually a family of hashing functions. SHA-3 is kind of what we use these days. It's newer, not prone to collisions. If you download like an ISO file from Cisco's website, they will oftentimes give you both an MD5 and a SHA hash. So you can use either one to verify the integrity of the data. So encryption is, changing data to something non-readable for transmission and then re-encrypted on the other end. A hash is used to verify the integrity. Hashing is not encrypting itself. It is just used to give yourself a fingerprint of this data so that you can verify its integrity and authenticity later. Okay, moving right along. So here's what hashes look like. Notice that I have different lengths of input, and yet my digests are all exactly the same size, right? And notice also the difference between these two. The red fox jumps over the blue dog. The red fox jumps hour. I've just had this one letter changed in this. And the hashing digest, the message digest, is vastly different. I just, FYI, grabbed this off of Wikipedia because it was just, I thought it was a really great example of all of this. And so changing just little bits will vastly change your digest. You're not going to get a repeat of this. This is going to come into play when we start talking about asymmetric encryption also. So let's get to that. Symmetric encryption, again, the same key is used to both encrypt and decrypt. It is fast. If you're going to be doing bulk encryption and bulk decryption, that's the way you want to go. You do have to have that pre-shared key, and AES is our prime example of that, of the algorithm itself. Now, how long does my key need to be? There's AES 256. There's AES, and you'll see this, AES 256. There's AES, 1024, 2048, 4096. You can get stupidly long with these key lengths. The way AES works also is, in addition to taking your data, the actual thing you're encrypting, and putting it into blocks, it will then also use different portions. Like it won't use the entire key every time it's doing a pass on encryption. It will use a portion of the key to encrypt different blocks. So this is one of the reasons it's really, really secure, is because it's, which portion of the key are you using to encrypt or decrypt any particular block, and it will switch lines between blocks, and there's all sorts of other fancy things it does, but it's really, really good. So comparing that to asymmetric encryption. With asymmetric encryption, we're going to have two keys. They are complementary. They are generated at the same time, and what is encrypted with one of the two keys can only be decrypted by the other key. You will hear of public-private keys, right? Public-private key pairs. When you have certificates, for instance, you'll talk about public-private key pairs. They're talking about two different keys. I could call them red key and blue key for all I care. It doesn't matter. The idea, though, is that one key, encrypting, can only be decrypted by the other key, and vice versa. I cannot encrypt and decrypt with the same key. So that sounds awesome. Why don't we just do that all the time? Because it is really slow. If you think about that, that means that I have to encrypt in such a way that only your key can decrypt, and it takes a lot more processing power to do the encryption and decryption when you're talking about asymmetric encryption. So how do we do this then? Symmetric encryption, our problem is that we need to share the key. What we're going to do with asymmetric encryption is go through a process where we pre-share a key using asymmetric encryption and then we do ongoing encryption and decryption with that symmetric key. And this is how, like, you know, again, online banking is the example I'm going to use. This is how that works. And that way we can do things securely, but also fast. So here we go. Now again, my drawing tablet's being a little funky. So let's see how this goes. All right, so I am at my computer over here, and I need to talk to my bank. Wow, this is really bad. Bank. So I'm going to open up a web browser on my computer, and I'm going to be typing in HTTPS. The S being, I would like to do encrypted communications. Okay, well, if we want to do encrypted communications, that means we're going to need to do a key. So what key do I use? I don't want to send the key in the clear because, you know, some bad guy in the middle here could, you know, get the key and then watch me pass my, you know, my account information and my password and all that good stuff. So here's what I'm going to do. I'm going to trust that at some point in the past, the bank went to a certificate authority. A certificate authority is an organization that starts trust. And by that I mean that there are certificate authorities out there. VeriSign's an example. And at some point, if I'm going to trust, I have to trust somebody. And so I'm going to choose to trust the certificate authority. So this is out, you know, on the internet. The bank went to the certificate authority and it said, please issue me a public-private key pair. Please issue me a certificate. So the CA generates two keys. One is public and one is private. And it gives the private certificate with the private key to the bank and to nobody else. It does not give it to anybody else. The certificate authorities, and I know that it has changed a bit, but certificate authorities generally don't even keep a copy of that private key, because if they get hacked, that would be a problem. Now, what the CA is going to do now is it's going to put the public certificate on its website. It's going to say, hey, here's a public key, a certificate which has a key in it that you can use. When I want to do online banking, HTTPS, I will go to the certificate authority. I will go to the bank and I'll say, hey, give me your public certificate. So the certificate authority will send me their certificate. So I have the certificate now. What am I going to do with it? Well, step one, what I need to do is verify that the certificate's good. Because again, what if, you know, bad guy in the middle here grabs the certificate being sent by my bank and then sends me something else bad? When the certificate authority generates the public key, it will also sign it. And by signing it, what it's going to do is it's going to take a hash. And that hash is going to verify the integrity of the certificate. Okay, well, can't the bad guy just grab the certificate, change the information, regenerate the hash, and then send me the bad data? Yeah, but the certificate authority is going to then go and use its own certificate, its own key, to encrypt the hash itself. So even if the bad guy could capture the certificate exchange, and even if the bad guy could generate a new certificate or modify the certificate and generate the hash, they could not replicate the signature. This means, though, at some point I have to trust somebody. The CA is going to have a root certificate. If you go into your browser and you go look, there's going to be a section in there on certificates. You can go in there and look, and you'll see root certificates that are trusted root certificates. And these are seeded by, you can get them if you've got a Windows PC and you connect to a Windows domain, they'll generally give you that The browsers themselves, when you download the browsers, they'll implement some of the root certificates that you can at least start the web of trust. You have to trust somebody. So I'm going to trust the certificate authority. The certificate authority has its own public-private key. It will have signed that hash with its private key, and then the public key, with the public certificate, it makes available. And this is the root certificate that I will download into my PC. So I get the cert. I go look at the signature, and I can decrypt based on the public certificate. They will have, the certificate authority encrypted the digital signature with their own private key. I will take their root CA and I will decrypt this signature, and then I will run a hash on the certificate, and those hashes better match. And if they don't, I know I have a bad cert. If the hashes match, then I can believe that there is no bad guy in the middle and that what the bank sent me is sufficient. So great. So now I've got a certificate. The certificate has a key that I can use to encrypt or decrypt. They have their key, which is the other half of that public-private key pair, and off we go. Great. We now have a pair of keys and we can encrypt. But as I mentioned, doing asymmetric encryption, because that's what I can do so far, right? Asymmetric encryption is really slow. And if I'm going to do bulk transactions, I need to speed it up somehow. So what my PC is going to do next is I am going to generate a symmetric key. And notice that it's my PC that's generating the symmetric key, and this is the session key. For this session of online banking, I am going to generate a key. And what I'm going to do is sign that key, the symmetric key, with the public key that I was given for the bank. And then I will send them now, of course, gibberish. The bank, the only thing that can decrypt this is the bank's private key. So I get this to them, excuse me, they will decrypt it, and then they will be able to do encryption with me. Oh, so how do we verify that they're still them? How do we verify that they got the symmetric key? How do we verify this? Along with the symmetric key, I'm also going to be sending something called a nonce. And really what this is, it's just a little hunk of code. And that little hunk of code is going to be encrypted with the symmetric key. So I'm going to send you the key, and I'm going to also send you this thing. The bank decrypts the symmetric key, uses it to decrypt the nonce. The bank re-encrypts the nonce with its private key and sends it back to me. This proves to me that they have the symmetric key, because if not, they would not have been able to decrypt the nonce. And because they can now re-encrypt it with something that only I can decrypt or somebody else can decrypt, I know that they have my session in mind. At this point, we have a pre-shared symmetric key, and we do symmetric encryption. A lot of stuff there. Who has questions? I mean, do you guys have any questions about how all of this works? Any other, any terms that you're not particularly happy with so far? Not hearing anybody. I'm going to go ahead and continue then. All right. So the certificate authority, they are the trusted keeper of certificates, and they are the root of trust. At some point, I have to trust somebody. I'm going to trust my certificate authority. Certificate authorities can either be public, and again, VeriSign is a good example of that. You can also have a private certificate authority. As an example, if you have a Microsoft implementation and you've got Active Directory and all the other good things that come with Microsoft server sets, you can designate one of those as a certificate authority internal to your organization. And as long as my PC, can get that root certificate of that, excuse me, of that, that certificate authority that's internal to my organization, then I can trust anything signed with that public certificate, or with that certificate, the private certificate that I just generated. And I can have a certificate inside my organization, a certificate authority inside my organization. I can have its root certificate signed by a public. So I'm going to be the root of trust inside my enterprise. But if you happen to be outside the enterprise, you can still verify that I am who I say I am. Think about trying to connect to a VPN, certificate-based VPN. I need to be able to verify that this random thing I'm trying to connect to, and the certificate it sends me to do encryption and decryption is who they say they are. How can I verify? Again, the public certificate. At some point, we have to trust somebody, and this is what our certificate authorities are about. There are certificate authorities, and then there are, what's the word for it? It's a certificate authority will then, the root will then sign another, it's not subsequent. What is the word I'm looking for? Well, a sub authority. I have the root, and especially if I've got the root CA inside my organization, I am not going to have it talk to anything. I'm going to sign it. I'm going to take it offline, not connect it to anything. I will take it out once a year to make sure the certificate gets renewed. Other than that, I'm not going to have it talk to anybody. What I am going to have it do is have it sign a subordinate server's certificate. And then this is the one that I'm going to use. The root CA cert itself, I still have to get into my PCs, but then I can trust anything signed by any in what they call the certificate chain. Root CAs sign interim CAs, sign interim CAs, and eventually somebody is going to actually sign a certificate. And as long as I can trust the chain, the certificate chain, then I'm good to go. And it all comes down to I have to trust somebody in the end. You'll hear the term CSR, certificate signing request. And again, I'm going to do a demonstration of this in the session later on this afternoon. And that is just me going to my server and going, I'd like to get a certificate. There's a little process for generating a request. And again, you'll see it if you come to the afternoon session. It just looks like gibberish. But I will send that to the certificate authority, and they will use that information. And that what's built into that CSR are things like the name of my server, my personal information. I'm talking about personal as in corporate. So, I'm Sunset Learning and our training facilities in Denver, Colorado, and this is the department. And there's something called subject alternate names, and a bunch of other pieces of information go into generating this CSR. It's formatted a very specific way. I send that to the certificate authority. They do their magic, create the public and private key pair, which will now contain that information that I had in my certificate signing request, and give me the certificates. And at that point, I now have the private key. The certificate signing request, what I do now is I download the private key. And remember, the CA stores the public key and this public certificate. So the CSR will generate a certificate. I then go back to my server and I will upload that certificate. And that means I have my root certificate now. I've got my signed certificate that other people can trust with my private key. The CA itself will make the public part of that public available. And so you can go get it. And using the process we just talked about, we'll be able to do per session encryption. So how do we distribute the keys? How do we distribute these certificates? There is PKI, Public Key Infrastructure. PKI, people talk about PKI certificates. PKI is not the certificates. PKI is the method of distribution for certificates. Who gets a private key? Where do I put public or public certificates and public keys? How do I give out certificates and public keys? Web of trust, open PGP. If you guys have heard of PGP, pretty good privacy. It was invented again back. It was invented by these guys. This one guy, actually, I don't remember his name off the top of my head. This one guy, and he's like, "Yeah, I don't really want to. I don't want to rely on a government agency of any kind to issue certificates. I don't want to rely on them to do encryption, because can I really trust the government?" And whether you believe in that sort of thing or not, and there's certainly a case to be made for it, excuse me, is there another way? With PGP, pretty good privacy, you and I will agree that we are going to be sending each other emails. I will use the PGP program to locally, at my own PC, generate the public certificate and the private certificate, the public key and the private key. And I'll put my little private key and I'll put it on, some kind of media and go lock it in a safe somewhere. I'll have a copy on my PC, but that, I have it there. And then I'm going to give you the public certificate. I will manually send it to you somehow. I can email it to you. I can physically give it to you. It depends on, how much trust you got there. But giving you that key and that certificate, I'm telling you that you're able to talk to me. And this is the web of trust, because we have to, we're talking about manual, excuse me, I got a cough. We're talking about manual exchange of these certificates. So web of trust. I trust you, you trust Bob. You tell me I can trust Bob, and so I go ahead and do so, and then we exchange, keys, and web of trust. There is coming a problem with OpenPGP in that. So I trust you and you trust Bob. So you're going to send me Bob's certificate, but how do I trust? Again, I don't have a man in the middle attack. Well, you're going to sign Bob's public certificate with your key, which I already trust. Well, then Bob also trusts Sue, and Sue trusts Chris, and et cetera, et cetera, et cetera. The number of subsequent signatures on these certificates is getting to the point where it's starting to be a problem. And they've already hit one of those milestones, and you have to go read up on exactly how they're getting around it. But there is actually a problem coming with OpenPGP currently. When we talk about certificate authorities and we talk about public-private key and certificate trust or certificate chain of trusts and all that, we're talking about centralized PKI, and this is the certificate authorities. Newer kid on the block are the blockchains. You've heard this term blockchain. With blockchain, it's an open ledger. Every transaction is recorded in multiple places using the same algorithms. And because of this, there is no one place to attack to compromise either the keychain or the trust list. I mean, theoretically, somebody could go into VeriSign, hack their master root certificate authority, and then we'd all be stuck. And there are root certificates that have been compromised. You'll see a certificate revocation list, again, if you go into your browser and take a look. But that's because there is, at some point, a single root. With blockchain, when a transaction happens and it is signed, that is copied to multiple ledgers. So there's no one place that all this stuff lives. Even if I could manage to compromise one of the repositories of blockchain transaction signatures, I can't do them all. And if I corrupt one of them, the others will reject it, because they do have, and they can verify amongst each other, the ledgers of these transactions. So blockchain, and then, that's just for transactionally. I'm thinking about things like, purchasing something with man, I'm having a senior moment today. What's like the famous cryptocurrency? Bitcoin. Thank you. My husband just piped up. Bitcoin. Exactly. So Bitcoin, and there's Earthreal, and there's a bunch of other cryptocurrencies out there, and they use blockchain. And again, because I don't rely on a banking system, which may or may not be regulated by a government agency, because I am not relying on a certificate authority like VeriSign, which is subject to regulations by authorities. This means that it is a non-authority based way of verifying transactions. So it's just a third way of distributing information. So where does encryption actually happen? When we talk about things like HTTPS, think about the TCP/IP protocol stack, right? I've got layer 1, and I've got layer 2, and this is going to be something like Ethernet or MPLS or something like that. I've got layer 3. This is going to be IP. I've got layer 4, and this is TCP or UDP. And then I've got layer 5, and this is your application layer. And we're not talking about your desktop application. When we talk about application layer protocols, we're not talking about Firefox. We're talking about the protocol that Firefox uses. HTTP, HTTPS, these are examples of application layer protocols. If you're talking about email, your email client, your application might be Outlook, or it might be Gmail, or whatever it's going to be. How do I exchange emails? I use a protocol for sending and receiving emails like SMTP or POP3 or IMAP4. These are the application layer protocols that my desktop application uses. So just a distinction there. The reason this is important is by indicating HTTPS, what I'm telling my browser is that I would like to use the HTTP protocol, Hypertext Transfer Protocol, but I want to do it in a secure manner. I want to do encryption. So what that's going to do is cause my browser to, at layer 4, at the TCP layer, start the encryption process. And this is where TLS comes in, Transport Layer Security. That's what TLS stands for, is Transport Layer Security. This means it's a per session way of having two applications at two remote locations find a way to do secure encryption with each other. When I did my example of online banking, I'm going to type in HTTPS and then the URL of my bank. Because I typed in HTTPS, my browser is going to use the TLS, Transport Layer Security, to start that process of doing the certificate exchange and the encryption of the nonce and the symmetric key and all that. The TLS is the process that we use at layer 4 to do HTTPS. And I make this distinction because it's important when you're reading documentation and you run across a term. It's like, what does that actually mean? Where is it? What you may have heard a lot about Ssl and Tls in the news over the last couple of years. SSL, secure socket layer, older, and not as secure. It finally was mature enough that somebody hacked it, so we don't use it anymore. It's vulnerable. And even with TLS, there's TLS 1.1, 1.2, and 1.3, and even TLS 1.1, which is an improvement over SSL, is now also vulnerable. If you can, you're going to want to use TLS 1.3 these days, and it's better. We were talking about DES and triple DES. SSL supported those, and 1.1 surprisingly still did, but not anymore. So TLS 1.3 is what my computer and my application use at layer 4 to do HTTPS, to do the S part of HTTPS. So all these things work together. So TLS, transport layer security. If you think about a socket, if you networking, generically networking socket, we're talking about an IP address and a port number. It gives me a connection between my application on my computer and your application on your computer. So with regards to TLS, that's what we're talking about. My desktop application, Firefox, is doing a secure session with the web server that is my online banking, right? So application to application, host to, not just host to host, not just PC to PC, but the actual application inside the PC to their application on their PC. That is different than setting up some kind of a tunnel, IPsec. IPsec is the PC itself. It's the computer having an encrypted connection to some other device. And all traffic for all applications can flow over this connection. Once the connection is established, then it doesn't matter, which of my desktop applications I'm using, I go through. When we talk about things like site-to-site VPNs, they often use IPsec to do their business. And what I'll have is the router at my office, right, over the internet, talking to the router at my the headquarters, and we're going to set up an IPsec tunnel here. Why? Because then it doesn't matter which PC for which person is talking to which business application at wherever in headquarters. Everything can flow over this tunnel, this IPsec tunnel. So it's a device-to-device tunnel that will allow all sorts of conversations to go over it. Site-to-site VPNs, that's that kind of thing. Host-to-host VPN is not really any different. Now I'm talking about like my PC talking to your PC. Can we set up a PC to PC connection? That's a host-to-host VPN, or host to device. And if you have a your laptop and you're setting up a VPN to your corporate network, that's going to be basically host to device. Your device host-to-host is your PC. The thing I'm encrypting with is going to be a firewall. But that's really sort of a host-to-host VPN. And then again, that gives me access into my corporate network. So this is at layer 4. TLS and SSL give me encryption at layer 4. We're talking about the desktop application. IPsec, really, we're talking about layer 3. It's an IP secure tunnel. So device to device, because my device only has one IP, at least with IPv4. So device to device. There is also layer 2 encryption. MPLS is a little less used than it was at one time, but layer 2 VPNs allowing me to do an encryption on a hop-to-hop basis. So each hop is I'm going to encrypt not just the data and then throw an IPsec header on it. What I'm going to do is actually encrypt the entire IP packet and then tack on some kind of a layer 2 header, which will include encryption information. And that way, I send it from me to the next hop, me to the router to another router, whatever. And that router will decrypt it, have the original IP packet back. And then as it's sending it out, its next hop will encrypt the entire IP packet and all of its headers, slap on a new layer 2 header, with encryption information, and so hop to hop. So that's layer 2 encryption. You can do all of these. You can do one of these. The more times you do encryption, the bigger your traffic gets, and so MTUs come into play. But this is just it's an overview, and there's way more to it. This is really just getting your feet grounded in what is encryption, how does it work, what are some of the different kinds of encryption. It can get even more complicated than this if you really start digging in. So this is Cisco Collaboration, my CCIEs and Collab. And this is Collab webinars. So how does all of this work with regards to Cisco collaboration devices? You will have heard the term security by default. And SBD, they just call it SBD these days. SBD, security by default. And what they're talking about is this. So I have a device, I have a phone, and I've got my call manager cluster. Now my phone's going to wake up. I take it out of the box. I put it together. Excuse me, I'm going to cough again. I'm going to take it out of the box. I'm going to put it together. And then now I need to go and I need to register with the call manager. So I have to go through my process. I'm going to go, DHCP and blah, 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 hit the TFTP server. How can I verify that the TFTP server that I'm going to be talking to is sending me good information? That's a good question, because I could certainly have a bad guy somewhere in my network misdirecting phones and getting them to register or get bad firmware, for instance. So how do I do this? Well, in the first place, let's talk about firmware specifically. In your phone, you've got flash. So that's basically your hard drive. So you've got flash. The flash has two partitions. There's the factory preset partition, and then there's the blank writable partition. One of the things that's in the factory preset partition on a Cisco IP phone is the public certificate for Cisco. So Cisco's public certificate. When I have my Cisco Unified Communications Manager and I have firmware, these firmwares, if you look at them, they are, the name of the firmware, blah, 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 .sgn. They always end in .sgn. And what they're talking about is that firmware has been signed. When Cisco creates a new firmware, it will sign it with its private certificate and then make that available. When I build a call manager server, all of those firmwares are in the servers, and I can make them available when I activate the TFTP service. Because the phone has Cisco's public certificate built into it, when the TFTP server says, hey, here's a new firmware for you, the public certificate can verify the signature of the private certificate for the firmware. So I can verify that that firmware is good before I try to download it. This is part of security by default. But how do I actually trust the TFTP server? Couldn't I have some random bad guy, again, stand up a call manager server and it's legit firmware? But how do I make sure that that TFTP server itself is an okay thing to talk to? Truth answer is you don't. When you take a phone out of the box, again, you have to start your chain of trust somewhere. And so when you take your phone out of the box and you boot it up that first time and it goes and talks to a TFTP server, that TFTP server better be legit. It's going to be. But then from there, once I do that first, leap of faith and I trust that first TFTP server, how do I now make sure that I'm able to trust other things? This is where these things come in: TVS, ITLs, and we're going to be talking about CTLs here in just a second. First of all, TVS, Trust Verification Service. This is a service made available by Cisco servers, TFTP specifically. And what this service provides is the ability for phones to verify things that the TFTP server are telling it. It means that the phones don't have to download the full certificates, because actual certificates are pretty big. But if the phone were to download the certificate for, excuse me, for, I've got a pub and I've got, 6 subs and I've got 3 TFTP servers and I've got a conference bridge and I've got a CTI manager server and I've got, a dozen different servers in my call manager cluster. A dozen different certificates, it's more than really I want to download into my phone. So what the Trust Verification Service does is it works with the initial trust list. The initial trust list generated by CUCM when the TFTP service is activated. It does include the full server certificate of the TFTP server, but it also includes a list of servers and a portion of their certificates that the phone should trust. So I download that now into the phone, and you can go and look at the ITL on the phone, and it's got well, you'll see the hash. You don't necessarily see all the stuff, but contained in the ITL is a list of certificates and the partial information about all the servers, including for each server a hashed signature. So again, thinking about using the hashing function to verify identity. I need to go and talk to a conference bridge, or I need to go and talk to a different TFTP server. I need to go talk to something. When I talk to that server, I can go and the server is going to communicate a piece of information to me. I can then go to the trust verification service and I can say, hey, this guy is trying to tell me that I should trust them. Can I trust them? And the trust verification service behind the scenes will now do the full authentication authorization of the server itself, and that it's allowed to talk to the phone. And then go back to the phone and say, yeah, go ahead, it's good. I have to trust somebody, so I trust the TFTP server. The TFTP server generates this ITL, and I download the ITL into the phone. I also download the TVS into the phone. And between those two things, I can now verify the identities and security of all of the servers in my cluster. This is why also, by the way, if you are in an organization that has more than one cluster, if I take a phone and I move it from cluster A over to cluster B, that's a different cluster. It's got a different set of servers. It's got a different server providing the TVS service. It's got a different TFTP server that generated a different ITL. And when this phone now goes and tries to talk to the TFTP server on cluster B, the TFTP server is going to say, hey, this is me. And I'm not going to be able to match it to anything that I have downloaded, me, the phone. What you need to do when you are moving a phone from cluster A over to cluster B is delete the initial trust list. And then when it goes over to the new cluster, it will start this process over again and download a new ITL. One last thing I want to talk about with regards to ITL is this guy, the Itl Recovery Certificate. So you stand up your call manager cluster. It generates a bunch of certificates, and again, we'll talk about those in the afternoon session. And great, I've got phones registered, things are groovy. I now need to make a change. Maybe I'm going to start signing my call manager certificates with a certificate authority. That's going to change the certificates. By changing the certificates, I am now changing the information that should be in the initial trust list. So I sign a certificate for a server. The information the server is now generating when the phone wants to talk to it doesn't match what the phone believes anymore. And so what the phone can do is, or really what the server can say is, hey, I'm new out here. And the Itl Recovery Certificate doesn't really change. It is a signature, and as long as the new server with the new certificate still has the same Itl Recovery Certificate, then the phone can go and use that to say, is this legit? The Itl Recovery Certificate will verify that this new certificate that I'm told to trust is good, and then the phone can trust it. What will happen at that point is a new ITL gets generated, and the phone, and it's actually a little more complicated than all of that, but the phone basically gets, anytime a certificate changes, the ITL changes, the phone gets a new ITL, and it can verify the old ITL and the new ITL that it should change it based on this guy. For anybody who has done a rollback to pre-8 before they did security by default, what you're doing is blanking out the Itl recovery certificate, making it null, which means it'll trust anything at that point. And that's how you can do mass migrations of phones to new systems. Which brings us to the certificate trust list. Now, the ITL and the TVS don't do encryption. Other than verifying the identity of the different components in my call manager cluster, TVS and ITL don't do encryption itself. But what if I do want to do encryption? What if I would like my phone, the actual phone itself, to have its own certificate so that it can do authenticated and or encrypted communications with something else? In that case, I need to issue this phone a certificate. That certificate has to be signed by something that both the phone and the call manager trust, and the other third party that I'm trying to talk to. And that's what the certificate trust list does. The CTL itself gets downloaded into the phone along with the certificate. So the phone gets a certificate. The phone also gets a CTL. The CTL is just like the ITL is, contains the same sort of information. It's just a bigger, beefier. It's the information has more certificate-related information about each one of the servers, including things like the signatures and the public keys and all this that the phone can then use to talk to those systems. So certificates, either full server certificate or just the token itself, which is the key for the call manager servers, the TFTP servers, alternate TFTP servers, the CAPF function. CAPF stands for Certificate Authority Proxy Function. This is the function, the service on a call manager server where the call manager needs to start handing out certificates. It is the proxy for the certificate authority. The call manager is. The certificate authority may be the call manager server or may be a different server, but call manager itself is a proxy for that because it's call manager that's going to be generating the certificates for the individual phones. Anything else I want to say about that? Nope, not really. Actually, one last little piece before I go. So today I'm doing this webinar, and then I'm going to be talking about later on today what are all the certificates that I see if I go to the operating system on a call manager and look at them. There's a lot of them in there. What are they? I'm going to demonstrate a certificate signing request and all that. Tomorrow, bulk certificate management. I have, there are 8 different certificates on 12 different servers, and I've got IMP, and I've got CUC, and I've got routers, and I've got firewalls and all this. Bulk certificate management. I don't want to one by one have to exchange certificates between systems. How can I do it in bulk? And certificate management in general. And then the other sub-webinar I'm giving tomorrow is talking about ICE and stun and turn. This has to do with Expressway. If you've heard of Cisco Expressway, that allows devices that are off-prem to securely communicate with on-prem systems like Call Manager without having to have a VPN. That's what Expressway does, basically. This is, these things here are encryption related. At some point, if I'm sending something encrypted, it has to get decrypted someplace. Where is that and how is that negotiated? That's what these terms mean. I'm going to be talking more about certificate trust lists when I do that one. That one's in tomorrow afternoon. And that brings me to the end of my hour. I actually ran a little long. I hope that's okay. And thank you for coming. I hope you come to more of these.